Turns out somebody stole my coffee. No coffee, no worky. I was wrongly accused and arrested for such a crime. It wasn't a pretty thing, but thankfully we gathered a little evidence. The suspects are Mrs. Jagger, Mr. D, and Miss Rouet. It looks like these got turned sideways on here for some reason. And thankfully, they let me go. Yay! I didn't do it. So, here's what happens. It turns out that there were 3 chemicals left at the crime scene where my coffee was taken. And then the police went to each of these suspects' homes, and they found some chemicals left at their home. So each of these guys had some chemicals at their home. And what we're going to do is we're going to use something called light spectroscopy to sort of figure out which of the chemicals were at the crime scene. So, for example, if all the chemicals matched Mr. D, we would know that those chemicals probably could have come from his home. Or if all the chemicals match Rue, we would know that they came from her home possibly, and they tracked it in at the crime scene. Or from Jagger, if all they came from Jagger's house, we would be able to track it back that way. If you pause this video and copy in that URL, you can actually see what kind of pattern you get when you burn any atom on the periodic table. Every atom gives off a unique color, and so this lab's based on this principle. So, who took my coffee? You can read that page, the handout, and then what we're going to do is we're going to draw a lithium atom, and then we're going to draw a sodium atom. We're going to answer a couple questions based on that. So, if we draw each atom here, and I'm going to sketch kind of quickly here. So I'm not going to write the number of protons and neutrons in there. I'm going to go kind of quick here. So there would be the nucleus. I'll just write 3 because it has 3 protons. The next shell would have, the first shell for electrons would have 2 on that shell, and we'd have 1 on this shell. Sodium would be basically the same, except it has 11 protons. So we're going to have the first shell. It's going to have 2. The next shell is going to have 8. And then we need 1 more for that 11th one. Okay. Now, general rule. The further away from the nucleus you get, the more energy they have. So as I move away from the nucleus, electrons have additional amounts of energy. So it'll be a small amount of energy inside and a large amount the further out you go. So same idea over here, more energy as you move further out. So, question, which of these 2 electrons has the most energy? And the answer would be the one on sodium because it's further away from the nucleus. So the general rule is the further away from the nucleus the electrons are, the more energy they have. By adding heat, we can temporarily make electrons jump to higher energy levels. So, if I zoom in here, if I add some heat to this atom, fire, what will happen is these electrons can actually move up temporarily to another energy level. So that electron could move up. This electron right here could move up, for example. And actually, we can even add another layer here. And this electron here could move up to a new valence layer. Okay? So when we add heat, it makes the electrons jump up to higher energy levels. Now, key point number 3 down here. When the electron loses energy, it'll fall back down to its original energy level. By the way, that is called a ground state. Okay? And when that happens, energy is given off in the form of light. So if we go back up to the lithium atom here, what will eventually happen is these electrons that were up here will eventually fall back down. They'll go back down to where they originally were. And when they do that, they will give off a light pattern that you can see. Okay. Now the cool thing is that every single atom in the universe that we know of gives off a unique light pattern. So for example, if sodium had the same thing happen, has a different number of electrons and they're in different locations, so it gives off a different light pattern. So when we heat sodium and see the electrons bounce up and then bounce back down, it'll have a different pattern than a lithium atom would have. And so that's the premise of this lab, or the point of this lab. These are the items we used. You're just going to make a key over the procedures, draw little pictures over here showing me that you understand each thing. Here's where students collected data. This would be the original color of the atoms. We went through each station of all of these. These were the ones found at each person's home. And then these down here, right here, are the ones that were found at the crime scene. So, for example, you'd tell me the color of the of copper nitrate. You'd tell me if it was crystal or powder form. You'd tell me the color, what it was when it was heated, and this is whose house we found it at, Rue's. We'll go through all 9 of those, and you'll also go to the crime scene, and you'll repeat the same thing, and you'll try to match the chemicals found at the crime scene to the ones that are listed above, and hopefully get a conviction for one of those teachers. Then there's some questions to answer, and that's the end of the lab.